Hello, everyone, and welcome back. Today, we're going to be talking about how we analyze proportions. Proportions are simply measurements from a statistical sample in which the value that we're estimating from the sample is the fraction of individuals in that sample that have a particular attribute. So typically, we're talking about nominal data here. And in this example that I'm showing here, it's a particular type of nominal data where there's two different values or states that each observation could take. And so in our example that we've been working through of the proportion of right-handed toads in our sample, here we have our example where we had 18 observations of the handedness of toads, and 14 out of those 18 observations were right-handed. Okay, so from this statistical sample then, we can calculate this parameter p hat. P corresponds to the proportion that we're trying to estimate or calculate, and the hat just refers to the fact that this is a parameter, okay? And so this is our estimate from our statistical sample of what the proportion of right-handed toads is in the population. So the way that we calculate the proportion of right-handed toads, or the proportion from our statistical sample, is that we take the number of successes, that's denoted by the symbol X, and divide it by our sample size. So in this case, we had 14 out of 18 right-handed toads, and so our estimate of the proportion of right-handed toads in the population is 0.78. And we can use this estimate of the proportion of right-handed toads from our statistical sample to try and draw some conclusions about whether the frequency of right-handedness in the population differs from our null hypothesis, which was 50-50. And to do this in our example of hypothesis testing, we use the probabilities that were generated from simulations where we simulated our sampling distribution, and we generated this empirical sampling distribution with thousands and thousands of replicates of repeated samples to use these probabilities to draw some conclusions about the frequency of right-handedness in the population. But if you recall, when we were talking about this way of testing null hypotheses, I mentioned that this is kind of the brute force approach, this sort of generating a sampling distribution by creating data and seeing how frequently they have 9 right-handed toads in a sample of 18 and so on. And we skipped over this idea that statisticians have spent a lot of time sorting out how we might derive equations from first principles to calculate these probabilities directly, rather than having to simulate them by randomly drawing samples over and over and over again. So the distribution that we're going to be talking about in analyzing our proportions then is referred to as the binomial distribution. And the binomial distribution then provides a probability distribution for the number of successes in a fixed number of independent trials. So in our sample of 18 observations, how many of those do we expect to be successes given a certain null hypothesis? Now, this binomial distribution is appropriate when we have either successes or failures. An observation can either be right-handed or left-handed. And there are also some assumptions that go along with this binomial distribution. First of all, that each trial or observation within the sample is independent of all of the others. That the number of trials in our sample is represented by n, and that the probability of success, denoted by p, for each of those trials is fixed. Okay, so the probability doesn't change across observations within the sample. So since we're talking about successes and failures, or two possible outcomes for each observation, the first thing that might come to mind is the flip of a coin. So let's imagine we were flipping a coin and we defined our heads to be successes And because there's a head on one side of the coin and a tail on the other, then the probability of flipping heads is defined to be 0.5. So let's suppose we flip a coin 10 times. What is the probability that 5 out of those 10 coin flips are going to be heads? What is the probability of 7 out of 10 being heads? What is the probability of 8 out of 10 being heads? And so on. Well, this is what our binomial distribution allows us to calculate directly. And each of those calculated probabilities is depicted by this probability distribution. So this is the binomial distribution for a probability of success of 0.5 and a sample of 10 observations. Most of the time, we're going to get 5 out of 10 heads. In some rare cases, we might only get 1 or 0 out of 10 heads. And in some rare cases, we may get 9 out of 10 heads. Okay, so coin flipping is not a very ecological example. So what if we move to a little bit more of an ecological example? Say we were interested in the number of brown flycatchers that we are likely to get in a sample of 5 flycatchers. So if the frequency of brown flycatchers in the population is 0.8, the most likely outcome in a sample of 5 flycatchers is that 4 out of 5 will be brown, but it's possible to get 5 out of 5, 3 out of 5, and so on. So this frequency distribution here is calculated from a binomial distribution where the probability of getting a brown flycatcher is 0.8 and our sample size is 5. So what we want to do then is, instead of creating a sampling distribution through simulations where we repeatedly sample randomly from a known distribution, and we do that thousands of times to create an empirical observed sampling distribution, what we want to do now as an alternative is to calculate an exact probability using the equations that brilliant statisticians have developed over the years that tell us exactly what is the probability of getting a sample of 3 out of 5 brown flycatchers when the true population frequency of brown flycatchers is 0.8. How can we calculate that? Okay. So in a binomial distribution, then, we can describe the probability of getting X successes in a sample size of N using the following equation. Okay. In this equation, the probability of X represents the probability of getting X successes. Okay. So in our previous example, where a success was represented by a brown flycatcher, then this is, let's say, the probability of getting 3 brown flycatchers in our sample. Okay, this odd notation here is pronounced or said N choose X. So the probability of X successes is equal to N choose X times P raised to the power of X times 1 minus P raised to the power of N minus X. So what does this N choose X represent? So we calculate N choose X using what are called factorials, where N choose X is equal to N factorial divided by X factorial times N minus X factorial. So what is a factorial? Well, N factorial means to multiply N by N minus 1, by N minus 2, by N minus 3, yada, 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 until we get down to 3, 2, 1, etc. Okay? So as an example, 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1, which is equal to 720. Okay? There are some rules to remember with respect to factorials, and that is, first of all, that 0 factorial is equal to 1, and 1 factorial is equal to 1. Okay, now factorials can get out of hand pretty quickly. If you do the math, you can figure out that 5 factorial is equal to 120, but 10 factorial is equal to 3,628,800. So you can imagine that in a reasonable size sample, the calculations of these factorials could get out of control pretty quickly. So if we were to calculate n factorial in a sample of, say, 35 or 85 observations, this is going to be a huge number. Well, luckily, we don't really have to do that because we can use some tricks of math to simplify this equation a little bit. And I'm going to walk you through a little bit of an example of that. Okay, so let's say we had 18 successes out of 20 observations. Okay, so then we would have 20 choose 18. So to calculate this 20 choose 18, we would need to calculate 20 factorial divided by 18 factorial multiplied by 2 factorial. Okay, if we calculated each of these factorials separately, we would be getting some pretty huge numbers. But we're going to use a little trick instead. If you remember what our meaning of 20 factorial is, it's 20 times 19 times 18, etc., etc., etc. But what that means, 18 times 17 times 16, yada, yada, is actually the same as 18 factorial. Okay, so we can rewrite 20 factorial as 20 times 19 times 18 factorial. And we don't have to write out all of the rest. In fact, we don't even have to calculate all of the rest. Okay, because now that we've expanded what we mean by 20 factorial a little bit, we can do some simplification of this equation. And the 18 factorial in the numerator and the 18 factorial in the denominator cancel out, and now we've got a relatively simple calculation. This 20 choose 18 is simply equal to 20 times 19 divided by 2 factorial. So we can use these equations for the binomial distribution to calculate probabilities associated with observations that are as extreme or more extreme than what we observed from our statistical sample in order to test a hypothesis about what the actual frequency in the population might be. Okay, can we reject that null hypothesis based on our observations in a sample? Okay, and when we use these calculations of the probability from a binomial distribution to calculate a p-value to test a null hypothesis, then we're doing what's called a binomial test. Okay, and so we're going to work through a binomial test using our example of the frequency of left and right-handed toads in the population. If you recall, the null hypothesis was that left and right-handed toads were equally frequent in our population. The alternate hypothesis, on the other hand, was that left and right-handed toads differ in their frequency in the population. The researchers went out and they measured handedness in 18 different toads and observed that 14 out of 18 toads were right-handed, while 4 out of 18 toads were left-handed. So in order to calculate then the probability of getting observations as extreme or more extreme than 14 out of 18 right-handed toads, we need to sum together a whole bunch of probabilities. Our p-value then would be equal to the sum of the probability of getting 0 out of 18, 1 out of 18, 2 out of 18, 3 out of 18, and 4 out of 18 right-handed toads, as well as 14, 15, 16, 17, and 18 right-handed toads. Okay? So these observations here represent the probability of getting a value equal to or more extreme than our observed value at the upper tail, And because our alternate hypothesis was not directional, we need to also consider the probability of getting values as extreme or more extreme than our observed value on the other tail of the distribution at the lower end. Okay? And for each of these probabilities, then, we can calculate the probability of getting, say, 14 out of 18 observations in our sample as being right-handed. And we can use this calculation from the binomial distribution to calculate each of these probabilities. So we can calculate the probability of getting 0 out of 18 observations as being right-handed by 18 choose 0 multiplied by the null probability in this population raised to the power of the number of successes multiplied by 1 minus the null probability raised to the power of the number of failures. Okay? And we could use this, expand this out, and calculate this probability of getting 0 out of 18 right-handed toads when the true frequency of right-handed toads in the population is 0.5. Okay? So we can take this probability, sum it together with the probability of getting 1 out of 18, 2 out of 18, 3 out of 18, et cetera, to calculate our overall p-value. Now, this can be a little bit tedious, especially with some of those calculations, including factorials. And so we can use R to save ourselves a little bit of time. And we can simply calculate the probability from a binomial distribution of getting the value of 0, let's say, in a sample size of 18, where the null probability is 0.5. Okay? Here, instead of inserting a single value and getting a single probability, I'm indicating that I want probabilities for each value ranging from 0 to 4. And we're going to stick those 5 different probabilities into this object I've called lower.prob. We're going to do the same thing for the upper end of the distribution, where we're calculating probabilities for each of the number of successes ranging from 14 to 18. And we're going to save each of those probabilities into this object. And then to calculate our probability or our p-value in our binomial test, I'm just summing together all of these probabilities from the lower end of the distribution and the upper end of the distribution. Okay? And if we were to do this for this example, we would calculate a p-value for our binomial test of 0.03. Now, as it turns out, there's an even easier way to calculate this binomial test or the results of this binomial test, because there's a function already written in R that will allow us to do this. Okay? So we can use the binom.test function, where we specify the number of successes out of the total number of trials, where the null probability is indicated by the notation of p. And from this, we get a calculation of the probability of success from our sample, as well as a p-value, or the probability of getting a sample as extreme or more extreme than this if the null hypothesis is in fact true. We can use this p-value then to draw some inferences about what the proportion of right-handed toads is in the population. Remember, our null hypothesis was that the frequency of left and right-handed toads was equal. The probability of getting a sample like this or more extreme than this, if that's true, is actually very small. And if this p-value falls below our alpha or our significance level, then what we would do is to reject the null hypothesis and instead conclude that the frequency of left-handed and right-handed toads in the population is not equal to 0.5. In addition to providing an estimate of the proportion in the true population, our statistical sample can also allow us to quantify precision around that estimate as a standard error. So we can calculate the standard error of our estimate of the proportion using this equation that's shown here. And one thing that's quite interesting about this equation for standard error is nowhere in this equation will you find any measurement of deviation or how much each observation within the sample differs from each other observation. So this is really quite different from the standard errors that we would calculate in most other circumstances. The only terms that appear in this calculation for the standard error of our estimate of a proportion is p hat, our estimate from the sample, and n, our sample size. So the standard error of our estimate of a proportion is entirely determined by that proportion itself and the sample size. So what this means then is that our standard error of the estimate depends on what the estimate is when we're talking about proportions. Now, for proportions, they have limits on what the value can be. A proportion can't be less than 0, and it can't be greater than 1. It has to be between 0 and 1. And you can see that as our estimate of the proportion approaches either 0 or 1, our standard errors are shrinking down really small and getting very, very close to 0. Okay? Whereas when our estimate of the proportion is close to 0.5, that's when our standard error around that estimate is the greatest. Okay, so in summary then, we've been talking in this video about how we can use the binomial distribution and the equations for probabilities associated with a binomial distribution to express the probability of getting X successes from n random trials. A proportion that we calculate from our sample provides us with the best estimate of the population proportion, but there is of course uncertainty about what that best estimate actually is. We can calculate the precision around our estimated proportion using a standard error that's calculated directly from the proportion estimate and the sample size, where the standard error is the lowest when p hat is close to 0 or 1, and the standard error is highest when p hat is equal to 0.5. The binomial test then provides us with a tool to be able to compare our observed number of successes to what we would expect under the null hypothesis, and to use our equations for probabilities in the binomial distribution to calculate exact p-values using the binomial formula to test our null hypothesis using a binomial test.